So in this lecture and in the next few lectures, I will be talking about embedding into distribution of trees, which is different than embedding into trees or embedding into ultrametrics. Because when you embed into distribution of trees, it means that one tree is not enough. You need a bunch of trees, a couple of trees, because at each tree, something good happens for that. So when you take expectation, then in general, you reduce your distortion, the overall distortion. And that's the idea and motivation behind a very interesting paper by kunal Tulwar. He's working in differential privacy in Microsoft now, I think. And he's one of the authors of the paper that I'm describing, which has the title, A Tight Bound on Approximating Arbitrary Metrics by Tree Metrics. And so, what is the goal? The goal is to embed endpoint metric space into a distribution over dominating tree metrics, such that you have a stretch that expectation of that is order of log n, which is very small, and this is good. This is practical because the expectation is very, the distortion is so small. It is not polynomial, it's not exponential, it's just log n. And the diameter, like previous lectures, the diameter of the metric is 2 to the delta, and the metric V prime and D prime is set to dominate V and D if the distance between any two vertices is greater than U and V in the original metric. Because D prime is now the tree metric. So it's kind of induced metric. And another definition is that S and D alpha probabilistically approximate the metric if every metric in S dominates D. And so the expectation of overall the metrics of D prime of U and V, the expectation is less than alpha D U and V. So you need to know some definitions first before we prove anything, or because the language needs these definitions. So arcade decomposition is a partitioning of V into some clusters, for example, this cluster, but each one is centered around the vertex and having at most distance R. So we have a couple of clusters, and 2 to the delta is the radius, the diameter, and this is less than 2R. So a hierarchical cut decomposition is a sequence of delta plus 1 nested cut decomposition, D0, D1, D delta, such that this guy is just all of your vertices. And little by little, you go down until you have just singletons. For example, U, for example, V, just singletons. So let me give you an example to understand what I'm talking about. For example, a simple graph, just, U, A, and V. U and V are connected, it's an edge. We have Z, we have W, and these, all of them are some edges of the graph. So in the first decomposition, we have just one cluster. And in the next decomposition, we have, for example, this one and this one and this one and this one. Still, U and V are not separated. But in the next decomposition, U and V are cut, so they are separated. They are in different clusters. And finally, we have another decomposition that Z and W and everything are decoupled. So there is some level that U and V are decoupled. After a sequence of levels, then at some level, you will see that at level I, U and V are separated. And we want to reduce this to lower levels, because at lower levels it is better. Your expectation of the stretch can be bounded, and it's not big. And that's why we want to reduce the probability that an edge is cut at higher levels. I mean, higher I's. And so let's just do it. So as you know, the distance between... So we have at the D3 level, at the I equal to 2 level, we have a decomposition that has a weight of 2, 2. And in the first decomposition, unfortunately, we couldn't separate them. So W and Z in one cluster and A, U, V in another cluster. But in the next decomposition, we could say that A and U are now in another cluster and V is another cluster. And then this goes until you go to the singleton level, which all of the vertices are just disjoints. So here you have W, you have Z. And this is the lowest level, which we call it I equal to 0. And the vertices are D0. So D0, D1, D2, and finally all of your vertices, D3. And it is obvious that the distance between any two vertices is equal to, because this is 2 to the 2, 2 to the 1, 2 to the 1, 2 to the 1. So where is U? 2 to the 0. This one plus this one plus this one plus this one becomes 2 times 2 to the j. But j from 0 to the ith level, which is less than 2 to the I plus 2. So if you get this example, then everything from the rest of the lecture is just formal things, and it's so simple. And we say an edge U and V is at level I if U and V are first separated in decomposition DI. So U and V is at level 1 in the previous example. So the distance between U and V, the tree distance, becomes 2 times 2 to the 0 plus 2 to the 1, which is 6, and is less than 8. So let's just decompose your graph. So again, what is the goal? The goal is to find a random process to define a hierarchical cut decomposition such that probability that edge U and V is at level I decreases geometrically with I. So the algorithm is like this. At the first stage, we choose a random permutations of V1, V2, Vn. For example, PV1, then PV2, then PV3, a random permutation. And you know about permutation, I just recall that P of n of k permutation of n is n factorial to the n minus k factorial. And so there are different ways, and because we are just using all of the vertices, so it's just n factorial ways to create such a permutation. And after that, we choose beta in 1 and 2, such that, from the distribution 1 over x ln of 2, such that, so for example, P1, P of vertices 1, the first permutation is greater than that, and we are ordering the vertices. And for example, we have, let's say, this is the I plus 1, and for example, here is the P of 1. Here is the P of 2. But because P of 1 has priority over P of 2, then if you select all vertices, for example, even those that have intersection, then it is in this vertex, that this vertex, for example, is assigned to this P of 1. So P of 2 doesn't have a chance to get that. So it has to get other points other than the intersection points. So we are just covering all the space, but in an ordered way. And this is our random process, because first of all, your permutation is probabilistic. Second of all, your radius beta, this radius is less than beta. I will explain in the third and fourth step. In the third step, we just say that d delta, all of the vertices is d delta, and delta minus 1 is I. But in the fourth step, we say that while di plus 1 has non-singleton, it means it is not at level I equal to 0, non-singleton, we say that beta I 2 to the I, so we are just multiplying this beta, which is inside 1 and 2, we are just multiplying it by 2 to the I minus 1 to get your beta. So because this is probabilistic, so beta I is probabilistic as well. And then we have 2 for loops. That's why the implementation is order of n2 if you are careful. Of course, in general, it is order of n3, the implementation of this algorithm. But if you are very clever, you can do it with less than that. Let's say O and 2. And so for L equal to 1 till n, we do that for every cluster. We create a new cluster consists of all unassigned vertices in S closer than beta I. So this is less than beta I. This is less than beta I. We are at level I. You know, we have a hierarchical levels. I starting, for example, at I equal to 3, then we reduce it, I equal to 2. For example, here at I equal to 1 is this. For example, I equal to 1 is this. All I equal to 2, I equal to 1 is this level, smaller. I equal to 2 is just even smaller. And you just reduce your scales. And so we assign a vertex to the first vertex according to that permutation vertex, which are closer to U. And each child cluster consists of the set of vertices that is assigned to single vertex. And you should note that the center V, for example, center itself need to be in S. This one cluster may correspond to more than one cluster, and each inside a different level I plus 1 cluster. So let's just observe that the probability that some beta i's lies in x and x plus dx is equal to x ln2 d of x. So all unassigned vertices such that the distance between v and p and l is less than beta I, we assign it to p of l. For example, these are blue circles, have bigger radius, so this is less than beta I, but the next level may separate u and v. For example, u is here and v is here. At level 1, they're the first time that they are separated. So at level 1, they are separated, and the center, for example, is w. So we say that the center w settles edges. So this w settles the edges u and v, this edge u and v, at level I. If it is the first center to which at least one of u or v get assigned. And we should note that exactly one center settles any edge at any particular level. So we need another definition that says that center w cuts the edge u and v at level I if it settles at this level. But exactly one of u and v is assigned to w. So whenever w cuts an edge at level I, the tree length of edge is about 2 to the I plus 2. So the omega distance between u and v is equal to one is the indicator function of omega that cuts u and v. I said that in some level it will cut, if it definitely cut it at level I, and times 2 to the I plus 2, because it just happens once, so we can clearly say that the tree metric between u and v is now upper bounded by a sum over a different kind of metric, which we call it dtw metric of u and v, which we have just defined. And so we would love to minimize dtw u and v, because if we do this, if we just minimize this leads to the cut at lower levels, and this is what we want. So let's just break ties for the moment and arrange the vertices in order of increasing arbitrarily the distance from edge u and v. It means that if we have ws here, and your u is here, and your v is here, so u and v is an edge, and then of course they are inside another cluster, and this edge. So here we can use the triangular property of that. For example, this one is ws, the center is ws, which could be p of 1, for example. We are lucky, and the first one is what we want. And then after doing that, after breaking the ties and arrange it in order of increasing distance from the edge u and v. So for example, p of 1 is greater than p of 2 until p of, for example, 4, that this is ws. W of S. So this is the S